Today, we're looking at something that could totally flip the script on how we cool, well, everything. Our homes, data centers, you name it. It's called elastocaloric cooling, and you won't believe how simple the core idea is. So get this. Picture a special kind of metal. You stretch it, kind of like a high-tech rubber band, and it actually heats up. Then you let it go, it snaps back, and bam, it gets super cold. We're talking cold enough to be your next air conditioner. Now, this isn't just some cool science experiment. Think about it. The hotter the world gets, the more we crank up the AC. But, and here's the crazy part, the stuff inside our air conditioners, the refrigerants, they're often super potent greenhouse gases. So we're caught in this vicious cycle. Cooling ourselves down is actually heating the planet up. Elastocalorics might just be the way to break that loop. Yeah, the real villain here are the refrigerants. They have something called a high global warming potential, GWP for short. And what that means is they're just ridiculously good at trapping heat in the atmosphere. We're not talking a little bit better than CO2, we're talking thousands of times more powerful. So naturally, these things are getting banned, and the pressure is on to find a replacement like yesterday. And that's where solid-state cooling enters the picture. You know how your fridge works, right? It squishes a gas into a liquid and then lets it expand back. Well, solid-state systems throw that whole idea out. They use the physics of solid materials to pump heat around. That means no harmful gases to leak, no clunky, noisy compressors. It's a totally different way of thinking about cooling. The specific tech we're talking about is built on what's called the Elastocaloric effect. It's just the fancy science name for what we talked about at the very beginning. You know, a material getting hot and cold when you stretch it and let it go. And honestly, the best way to get it is with a really simple analogy. So check this out. It's basically a perfect mirror of how your AC already works. On one side, you've got the classic method. You put a gas under pressure, it turns to a liquid and spits out heat. Then you release that pressure, it boils back to a gas and sucks in heat. That's what makes things cold. Now look at the elastocaloric side. Applying stress to the solid, that's just like pressurizing the gas. It changes its internal structure, its phase, and releases heat. And releasing that stress, you guessed it, it's like releasing the pressure. The metal flips back, sucks in heat, and gets cold. Same principle, totally different medium. So what's actually going on inside the metal? Well, it's a phase change, but it's happening while the material stays solid. We're talking about special materials called shape memory alloys. Think of them as being able to arrange their atoms in two different ways, two different crystal structures. One is called austenite, the other is martensite. When you stretch the alloy, you literally force the atoms to rearrange from austenite to martensite, and that process kicks out a bunch of heat. Then when you let go, it snaps back to the austenite structure, and to do that, it has to pull all that heat back in from whatever's around it. And that's what makes it so incredibly... Okay, so that's the cool physics trick. But how do you actually build an air conditioner out of it? Well, you don't just stretch a single wire back and forth. You build what are called beds of these materials, just like you see here. Then you get a fluid involved. Something simple like water works to act as a heat taxi. When the material gets hot from stretching, one loop of water comes by and carries that heat away. Then, when it gets cold from releasing, a different loop of water brings the heat from your room over to be absorbed. All right, let's walk through the whole four-step dance. First, load. You stretch the alloy, it gets hot. Second, heat rejection. A fluid whisks that heat away. Third, unload. You release the stress, it snaps back and gets colder than it started. And fourth, heat absorption. A second fluid brings the heat from your room to the cold alloy. And then you just do it again, and again, and again. That's your continuous cooling. But wait a minute, this all sounds great, but it brings up a huge problem. Right? I mean, think about it. If you keep bending a paperclip, what happens? It snaps. That's metal fatigue. And for the longest time, this was the absolute killer for elastocaloric cooling. It was its Achilles heel. I mean, how are you supposed to build an AC unit that lasts 10 years if the heart of the system breaks after only a couple thousand stretches? And we're not talking about a small problem here. This was the roadblock, the main thing holding the whole idea back. Your home AC has to run for millions of cycles over its lifetime, not just a few thousand. So the entire future of this technology really hinged on one thing: figuring out how to stop these materials from breaking. And it turns out a huge part of the problem starts on a scale you can't even see. Look at the top image here. That's the edge of the metal as it's made. It looks rough, right? It's full of these tiny microscopic cracks and flaws. Every single one of those is like a little weak spot, a starting point for a bigger crack to grow. So every time you stretch and release it, the stress builds up right there. And eventually, snap. Now, look at the bottom image. That's after they've treated it. Big difference. So how did they fix it? Well, it took some pretty clever materials science. First, and this probably won't surprise you after that last image, is just good old-fashioned polishing. By making the surface incredibly smooth, you just get rid of those starting points for cracks. The second trick is a bit less intuitive. It's called pre-straining. Basically, you take the material and give it one really big stretch at the beginning, way more than it'll ever see in normal use. This seems to kind of train the material's internal structure, getting it all aligned and ready, which makes it way tougher against fatigue later on. And when you put those two things together, the results are, honestly, pretty staggering. Researchers have managed to push these materials to survive over 100,000 cycles without failing. Now, okay, that's not the millions of cycles you need for a commercial AC unit just yet, but it is a massive, massive leap. It shows that there's a real workable path to making these things last long enough for the real world. And here's the best part. They're not sacrificing performance to get that durability. Even with these super tough materials, they're still getting a temperature drop of 8 Kelvin. That's an 8 degrees Celsius drop, or about 14 degrees Fahrenheit, in the blink of an eye. That is some serious cooling power. It's more than enough to build a really effective cooling system. And all of this leads to the real holy grail, efficiency. In the world of cooling, this is measured by something called the coefficient of performance, or COP. It's just a simple number that tells you how much cooling you get for every unit of energy you put in. Your typical window AC unit might have a COP of, say, 2 or 3. Well, the models for these elastocaloric systems, they're showing they could hit a COP of 4, maybe even higher. That means way less electricity for the same amount of cool. So let's put it all together. You've got the potential for way higher efficiency, and you get rid of all those nasty refrigerant gases. When you see that combo, it's no wonder that a lot of experts are looking at this and saying, yeah, this is one of the most promising new technologies out there. We're not just talking about a slightly better air conditioner. This could be a genuine revolution in how we cool things. So here we are. The basic science is solid. The biggest engineering hurdle, that pesky fatigue problem, is being cracked. And the upside for our energy bills and the planet is just huge. We've watched this go from a weird little physics curiosity to a technology that feels like it's right on the edge of being real. So the question really isn't, can we do this anymore? The real question is, how soon will it be in our homes?